Today, we're presenting our final project for Data Science Laboratory. The project we did is a comparison of two reinforcement learning algorithms for autonomous highway driving. We trained PPO and SAC agents to navigate a busy multi-lane highway. This is a quick roadmap of what we'll cover today. We'll start by grounding the project in course concepts including neural nets, risk minimization, regression, and regularization. Then we'll walk through our environment setup, our custom reward function, how each algorithm works, and finally our results and conclusions. So the problem we tried to solve is, can a reinforcement learning agent learn safe, efficient highway driving entirely from raw sensor data with no hand-coded rules? And these were three challenges that we found in creating this project. Moving on to course concepts that we covered. Number 1, neural networks. Both PPO and SAC use a multi-layered perceptron. This is the same feed-forward neural network that we studied in class. The network takes in 30 numbers representing the sensor state of the world, passes them through hidden layers with nonlinear activations, and outputs two numbers, steering and throttle. Number 2, risk minimization and optimization. From what we learned in class, empirical risk minimization meant minimizing expected loss over a dataset. In reinforcement learning, it's the same concept, but over trajectories instead of labeled data. Number 3, regression. Both algorithms use the critic network, which is a regression model. Given a state, it predicts a single continuous number, which is the expected total future reward for that state. Finally, regularization. SAC has an explicit regularization term built into its objective, measuring the entropy of the policy. Entropy measures how spread out the action distribution is. By rewarding high entropy, SAC is penalized for becoming too confident too early on, and is forced to keep exploring. This is mathematically identical to L2 regularization, preventing a model from overfitting to training data.
The environment is highway-env, an open-source driving simulator. We have one vehicle for our agent and 15 to 20 other vehicles in the environment that are driven by the simulator. These vehicles follow simple traffic rules and react to each other. What the agent sees is a snapshot of the 5 nearest vehicles, including itself. For each vehicle, it gets 6 numbers: whether the vehicle is present, its x and y position, its x and y velocity, and its heading angle. That's 5 vehicles times 6 features, 30 total inputs to the neural network. We then normalize our raw values like position or speed so that the smallest possible value maps to 0 and the largest maps to 1. We did this because neural networks tend to train much better when inputs are on a consistent scale. If you feed in a raw speed of 28 meters per second alongside a binary presence flag of 1, the gradient update gets dominated by whichever feature has the largest magnitude. Normalizing puts everything on equal footing. For control, the agent outputs 2 continuous values between -1 and +1, one for steering and one for acceleration. This is what continuous action means. There is no discrete option of turn left, turn right, or brake. The agent outputs any real value in that range, giving it much finer control over the vehicle. The reward function is how we define what good driving means. The agent doesn't inherently know that staying in a lane is good. We have to tell it through the reward signal. Our function has 5 terms. The first one is speed reward. The agent gets up to +0.5 for going fast, scaled so that 30 meters per second is full reward and standing still is 0. The second one is lane reward. We measure the lateral distance from the center of the lane using the lane's local coordinate system and penalize deviation up to -0.4. The third one is collision, a hard -2 if the agent crashes, which usually ends the episode. And then we have 2 smaller penalties for jerky steering, one for sudden changes and one for holding a large steering angle. These 2 are to encourage smoother driving. The algorithm that we use is PPO, Proximal Policy Optimization. The agent runs its current policy, collects a batch of experience, and then updates. After the update, it throws the experience away and starts fresh. It never learns from old data. The key innovation in PPO is the clipped objective. When it updates, it calculates how much the new policy differs from the old one and clips that ratio at 0.2. This is the clip range equals 0.2 in our config. This prevents a single bad batch from catastrophically changing the policy. It's a conservative, stable update rule. We ran 4 parallel environments simultaneously to collect data faster. Each environment runs independently and the experiences get combined into one batch. We trained for 20,000 time steps total, which is relatively short. PPO needs a lot of data because it discards everything after each update. In practice, We saw PPO learn basic driving behavior quickly, but plateaued, which is expected given the limited training budget.
SAC stands for Soft Actor Critic, which is an off-policy technique that is fundamentally different. It stores every experience it's ever had in a replay buffer, and ours have held 200,000 steps and learns from random mini batches of that history on every update. Because it reuses data, it's dramatically more sample efficient. It is used to maximize reward and entropy to encourage exploration of the dynamic environment. This approach auto-tunes temperature alpha for best balancing exploration with exploitation. SAC also has two critics, not one. It trains both and takes the minimum of their predictions when computing the target value. This is a deliberate bias toward pessimism that prevents overestimation errors that tend to destabilize off-policy training. The entropy term we've discussed from the course concepts slide is baked directly into the objective. SAC maximizes reward plus entropy, and the temperature alpha, which we set to auto, is adjusted automatically using a second gradient descent to hit a target entropy level. When the policy is uncertain, it gets a very high alpha, encouraging exploration. As it learns to drive, alpha decays and the policy becomes more decisive. This slide here summarizes our training configuration. We've used 150,000 time steps with a learning rate of 3e to the negative 4 and a replay buffer size of 200,000. The batch size was set to 256 with gamma at 0.99 and tau at 0.005 to keep learning stable. We also used auto entropy coefficient tuning, and learning began after 2,000 steps to make sure the model had enough initial experience prior to updating. This slide shows our SAC, or Soft Actor Critic, training progress on the highway environment. In the early stages, the episode reward rises quickly from about 185 to 268, which shows the agent is learning an effective driving policy. At the same time, the entropy coefficient gradually decreases, meaning that the agent is shifting from more exploration towards more stable exploitation as training continues. This slide breaks down the training behavior of SAC across three key metrics. The actor loss keeps decreasing, which suggests that the policy is improving over time, while the critic loss drops and then levels off, suggesting that the value estimates are becoming more and more stable. At the same time, the cumulative gradient updates rise steadily, reflecting consistent learning throughout training. The training logs for the soft actor critic agent demonstrate successful convergence over the 20,000 time step duration. A steady upward trajectory in both the mean episode reward and episode length confirms that the agent is effectively learning to maximize its returns while surviving longer in the environment. While the actor and value losses exhibit the typical fluctuations of off-policy reinforcement learning, their general downward trend suggests that the model is accurately refining its internal estimates. Additionally, the entropy loss shows a consistent increase towards zero, which is a key benefit of SAC's mechanism for balancing exploration with exploitation. Finally, the low and stable approximate KL divergence indicates that policy updates remain controlled, preventing the training process from becoming unstable or collapsing. The SAC training results show highly promising early stage performance, highlighted by a 45% reward improvement within the first 2,400 steps. Operating at a training speed of 4 frames per second on a Mac CPU, the model is projected to reach 150,000 time steps in approximately 7 hours without experiencing any initial crashes. Key optimization metrics are trending correctly, with the critic loss dropping significantly from 3.0 to 0.66, indicating improved value estimation. Simultaneously, the entropy coefficient alpha has decreased from 0.965 to 0.67, showing the agent is naturally becoming more confident as it moves from exploration to exploitation. Overall, the stability of the actor loss and the lack of crashes suggest a robust hyperparameter configuration for this environment.
key structural difference is on policy versus off policy. PPO starts fresh every update. SAC learns from its entire history. That makes SAC harder to implement and tune, but far more data efficient. PPO is the go-to for quick prototyping and stable training, whereas SAC is the better choice for complex, continuous control tasks like this one. To summarize, both algorithms learn to drive from scratch with no hand-coded rules, which validates the approach. However, SAC showed faster early improvements thanks to off-policy training and entropy regularization, whereas PPO is simpler and more stable but needs more data.